Today, I'd like to introduce the Ethernet VPN, EVPN technology. In the cloud era, as data center DC services are gradually expanding, functions are becoming increasingly complex. To meet requirements for geographical redundancy and resource utilization improvement, multiple DC networks are deployed in different areas. This means that interconnection between DCs becomes the key issue. Virtual Private LAN Service, VPLS, an early MPLS VPN technology is widely used in DC interconnection scenarios and provides multi-point to multi-point MP to MP WAN Ethernet services for enterprise users. However, VPLS has the following disadvantages. First, MPLS must run on all devices, and full mesh connections must be set up network-wide. In cases where the network scale is particularly large, configuration and capacity expansion are complex. Second, MAC addresses are learned by MAC address flooding, which results in a large number of broadcast packets, wasting bandwidth resources. Third, VPLS does not support load balancing on multi-homing networks, so as to prevent loops. As the number of servers in the DC increases and the virtualization technology is widely applied, the number of MAC addresses on the Layer 2 network rises exponentially and the traffic volume keeps growing. As a result, problems with the VPLS technology become more and more salient. Therefore, VPLS is unable to adequately support the establishment of a modern large DC. Ethernet Virtual Private Network, EVPN, is the next-generation Layer 2 network interconnection technology used for DCs. EVPN uses multi-protocol extensions for BGP, MPBGP to transmit information such as the MAC addresses and IP addresses of network nodes and advertise MAC or IP address reachability. EVPN forwards Layer 2 or Layer 3 packets based on generated MAC address entries and route entries, implementing DC interconnection. Similar to the IP VPN technology, EVPN switches the MAC address learning and advertisement process from the data plane to the control plane. Currently, EVPN uses MPLS architecture-based RFC 7432 on the control plane. However, the encapsulation technologies used on the data plane vary according to application scenarios. For example, MPLS, PBB, and VXLAN are applicable. EVPN implements Layer 2 MAC and Layer 3 route forwarding by enhancing the control plane. The data plane processing depends on the negotiated channel type. So now let's look at the EVPN model. On the EVPN, to allow intercommunication between sites, an EVPN instance is created on each PE on the backbone network and then bound to the PE's interface that connects to the CE at the site. In addition, EVPN peer relationships are established between PEs and transmission tunnels are established between them on the data plane. When devices on the EVPN belong to the same autonomous system, AS, you can configure a route reflector RR to prevent IBGP peer relationships from being established between all PEs. In this case, the RR only advertises and receives EVPN routes, avoiding the need to encapsulate and decapsulate packets on the data plane. Configuring RRs helps minimize the complexity in network deployment. In EVPN networking, a CE/CE3 in the figure can be multi-homed to 2 or more PEs. The set of Ethernet links between the CE and different PEs is an Ethernet segment, ES. An ES must have a unique non-zero ID, that is, an ESI. The ESIs of multiple PEs connected to the same CE are the same. On an EVPN, PEs learn MAC addresses from CEs and forward the learned MAC addresses to other sites through EVPN routes. Now let's look at EVPN routes. BGP newly supports 5 types of routes for EVPN. First, Ethernet Auto-Discovery AD route. An Ethernet AD route advertises the reachability of the local PE to the MAC addresses of its connected sites. It is used for fast convergence, redundancy mode, alias, and split horizon. It solves the problem of load balancing on the multi-homing network. Second, MAC or IP advertisement route. In the EVPN solution, the MAC and IP addresses of a site are advertised through MAC or IP route advertisement routes. There is no need to flood ARP request packets network-wide, which greatly reduces the broadcast traffic volume on the network and therefore minimizes bandwidth consumption. Third, Inclusive Multicast Ethernet tag route. Inclusive multicast Ethernet tag routes advertise the reachability of broadcast, multicast, or unknown unicast BUM addresses to implement mutual neighbor discovery in the broadcast domain so that the local PE can send BUM traffic received from CEs to the remote PE. The routes also contain the attributes of tunnels to be established. The routes can be used to establish tunnels for transmitting data plane traffic between PEs. Fourth, Ethernet segment ES route. ES routes are used for PEs connecting to the same CE to automatically discover each other. The routes are used for designated forwarder DF election. When a CE is multi-homed to PEs, to prevent the CE from receiving duplicate traffic, only one PE is needed to forward BUM traffic to the CE. In this case, a PE must be elected based on a fixed algorithm of DF election among PEs in the same ES. Fifth, IP prefix advertisement route. An EVPN is a private network and can access an external network through IP prefix advertisement routes, which advertise the imported external routes. So now let's look at EVPN advantages. First, EVPN uses extended BGP to perform MAC address learning and advertisement on the control plane instead of on the data plane, managing MAC addresses and implementing load balancing. Second, by using the EVPN technology and the RR feature of BGP, PEs on the ISP backbone network do not need to establish full mesh connections. Instead, only RRs are deployed to reflect EVPN routes, reducing network deployment costs. Third, BGP is used to advertise MAC addresses to prevent MAC address flooding and save bandwidth resources. So, thank you for watching. Goodbye.